In part one, we broke down the brain of the drone, the flight controller. In part two, we covered the muscles, the motors. Today, we're talking about the nervous system of the aircraft, the ESCs, because this is the part most builders ignore. Until it fails, these small bores decide how cleanly power moves from your battery into your motors. And if they're undersized, misconfigured, or overheated, everything else just stops working in the aircraft.
And if you've ever wondered what those settings or the meaning of 4-in-1 or 45 amps or BL Heli 32 or Castle 3040, or some of the things I've said for the ESCs, and those specs actually mean, why ESCs get fried, or how to pick the right ones for your build or fleet, this episode is for you.
Yeah, so this is part 3 of our 7-part Inside the sUAS build series here on the Swarm News. So if you're following along, building your knowledge stack with us, grab your coffee and let's get into this. Welcome to Swarm News, where veterans and engineers talk about defensive tech the way that it actually works, not the way that it looks in a briefing. I'm Joshua here with my co-host Vince, and he's going to give us an update on what's going on in the UAS world.
And thank you, Josh. And for this week, kind of go over a couple of things in the military side of things, commercial, and just kind of give you guys some updates on what's going on. One of the new things we got that's kind of coming out from the Army is they just test fired a new 30mm Apex proximity fused, optimized for detonating just in front of the sUAS, so that it basically can stop the UAS before it gets to you. But it gives the Army more of a broader push to modernize its kinetic and sUAS or counter sUAS options. Another one is the JIATF 401 just released standard guidelines for test and evaluations for counter sUAS tech. They're trying to unify the data and performance metrics so that across all the vendors and programs, they have a system that can be compared and be given an apples to apples kind of overview of what they should be doing, and or for just the agencies to understand what they have. Another one from the JIATF-401, also having an industry day this month, what is a collaboration with all the companies out there. Basically, this collaboration will be seeing what we have for detection, tracking, and defeating systems, and emphasizing layered defense. And instead of just chasing a silver bullet, they'll have basically different layers for different systems so that they can manage the systems to meet what they need for requirements. On the commercial side, a Ukrainian company by the name of Skedaton has a new system that will detect radiation. If you don't know, is a Ukrainian-born UAS manufacturing company that just basically started to integrate a gamma radiation surveillance sensor into its Raybird UAS or sUAS. Is basically able to target long endurance. Because it's long endurance flight, it can basically evaluate and ensure that the environment that it's looking at doesn't have any radioactive hazards to it. So it can monitor and help with emergency responses so that you know what's out there in regards to radioactive hazards that may be around or any fallout. Another one is in the aspect of sUAS, the Pixhawks now have an option where a company by the name of Ground Control is meeting up with ArduPilot or with the writers or the coders for ArduPilot. The development teams from those two places are going to be coming out with a setup to where Mavlink telemetry can go over Iridium Certus 100 satellites devices. So this basically will allow Europe to support satellite communication and make it more reliable in connectivity through a sUAS, with those components being now a hub for connection between each other, which that's going to be a significant upgrade for a lot of sUAS. Like even for hobbyists now, if you are wanting something to be significantly able to communicate via 5G, satellite, or even just your regular ground station, you have opportunity to have 3 different redundant systems put into one, which is going to be amazing for anybody who does build stuff going forward. Another one, FAA and the CSA have finally published a BVLOS, or Beyond Visual Line of Sight, NPRM, and it's aimed at normalizing the routine for BVLOS ops in the NAS or national airspace, which is how the main policy document will cover what to watch if you're planning to scale beyond VLOS and how it's going to work in the US. So this is going to be a big one for all you guys who are trying to figure out ways to fly further and having to put in your waivers. This will help now cover a lot of the information that hasn't been really out there in the past on how it is expected to be done for BV loss, which is going to be helpful because now it's just a draft, but in the end, it should be coming out with a finalized product here any day or any time now. So with that, that's all I have for news for this week. You got anything else, Josh?
No, let's go ahead and get started with the basics again. Yeah.
Roger that.
So, for someone who hasn't dug into the electronic stacks before, what exactly is an ESC in context of like small UAS systems?
ESC stands for electronic speed controller. Its job is to take the DC power from the battery and turn it into a signal that can be read and understood by a three-phase signal brushless motor. It's basically the translator between the flight controller and the commands from from the flight controller going into the ESC and gives that command to the motor so the motor knows what it needs to do.
Okay. So, like the flight controller says spin faster or slow down on this corner. The ESC converts that command into a real electrical power going into the motors.
Yeah, exactly. The flight controller sends throttle command. The SC basically turns that into different signals from what it needs through power that's being given to it from the battery. And it turns that into a frequency or pulses that will then turn into a signal that is also a power rating on the other side for the motor to recognize and switches the pattern controls from that ESC into RPMs and torque and is doing this thousands of times a second pretty much.
Okay. So, the signal chain we've been building through this series that we've started is the radio, which is the flight controller, the ESC, and then the motor, and each layer handling control down to the next.
Right. So radio hasn't been going over as much, but that's going to be one of the next ones that we'll talk about. The radio gives the sensors basically what it needs to know, what you're expecting for it to do. The flight controller decides how each corner should respond. In other words, each motor is on knowledge of what it needs, and it goes through the ESC to do this. The ESCs are the power stage that actually delivers the current to the motor and gives the control the way it needs to be.
Okay. So, now, when people start building drones, they quickly notice ESCs come in a few different like formats, right? So, what is the main types that builders are going to see, and what's the difference?
Yeah, you have a couple big categories for what you look at for ESCs and just the physical state of the ESC. So when you look at it, you have something such as like this one, and I'll go from kind of top to bottom, where you have like all in one flight controller. You have the ESCs incorporated into the flight controller. And in that aspect of it, it saves you a lot of space and time. Only problem is if one of the ESCs stops working, you got to replace not only the flight control or the ESC, you got to replace the flight controller along with it. So that means you got to go through a complete tear down and set up and break out for what you needed to do in the future. Another one is that you have a stack. Typically, you have a all-in-one ESC that has four of them in one, or how many you need for whatever the aircraft, but typically you have the four in one, and that single board connects to a flight controller, and it gives all the signals to all the other motors, and it's just basically separated from the flight controller. Then you have another one, which is you have a just individual ESC. With this one, such as this, you have each one of those connected to each arm, and they're a separate individual ESC, which allows you to basically just replace one at a time if it breaks. Unlike with the other two, where you have a board that if one ESC stops working, you got to replace that whole thing. This one makes it a little bit simpler where you just replace that one component. The only problem is that now you have to add in more components, which in this case, to get this one ESC, you need to have a PDB, which is distributing the power from the battery to it and all the other components on the aircraft. In a lot of cases, for the all-in-one ESCs, they act as a PDB for your system, so you don't have to worry about having a separate component. So that means that it can run your power from the battery, to the flight controller and to your other subsystems that are on it. Whereas if you have individuals, now you have a separate board that you need to produce all the power, separate it out to the components on top of your flight controller. And then in some individual cases, you'll have ESCs that have power to them, or it has a BEC or a built-in electronic, basically its own power source into the ESC so it can provide its own power out. And normally ESCs like this are for planes and not for your typical quadcopters or your rotary wing drones, because this ESC can actually provide a source of power to your receiver and then also get power to the motor, and you don't have to worry about actually having a power source because it all runs in one. But it also doesn't always need a flight controller, but that's why with a plane is a little bit easier. You just give it throttle and you're up in the air and that's it. Versus a quadcopter is not the same. You need a flight controller to give the motors opportunity to know what they need to do.
Okay. So I just want to make sure I'm catching you. I want to make sure we're on the same page right now, right? So you're talking modular design or the independent components, which are going to be a little bit heavier. So you have the versus your like compact design, which is the 4-in-1 system. The problem is like you're giving up something on all of this, right? Like the components, you get only have to swap out a component that goes bad. But if you have the 4-in-1, you're basically starting over and have to redo everything because everything has to get resoldered and re-put back in, and it's more time consuming because you have to redo the flight controller also, right?
Correct.
Okay.
In a lot of cases, like if it's all in one, like this one, you have to redo everything from scratch. The one board that has just the ESCs, you don't have to do everything. You just have to replace the ESC out, that whole all in one, and your flight controller stays pretty much reset up. You just need to reset up the ESCs or calibrate them if need be, and you're back to going. The individuals, you just replace one, you calibrate it, and you're good to go. And it just simplifies it like that. And if you blow one and like an individual, it's easier just to replace it. Whereas the other ones, you have a lot of other, and there's some other factors you may have to go into it too, like you have to cool it. Cooling these down is a little bit easier because it can be out on the arm and the wind automatically naturally flows over and keeps it cool. Whereas your stack, you may have to add in a fan to it to help keep that cool, but it should be able to stay cool also with regular flight.
Okay. So what about like, so is the 4-in-1, would that also be considered an integrated FC plus ESC? Is that what that is? Or is
Um,
that something different? Are those like, are they the same, different? Can they be different or the same?
so if it's all in one, so it means, yes, you don't have to really do much to it. It all is there. It means that your amperage, all your settings, your protocols are in that one, whereas the others, they all have their protocols too, and they just act as an individual, which there's times where you have to go through the calibrations of it, which is another thing that you have to consider with it. You calibrate ESCs typically in order to make sure that they're synced in time. All in ones are easier because they're all set up to be synced in their own way. So you don't have to worry about the calibration as much or if at all. Whereas individuals, you do typically want to calibrate it so it'd be lined up with your power throttle rate or curve.
And what about AIOs?
Yeah, that's your all-in-ones. Your AOIs are, pretty popular in smaller quads and whoops. These are the ones that you pretty much use for time and just for space and weight. But it makes it a little easier to put something all in one because it's less weight. And whoops and basically small drones will work easier with those. You get fewer cables, a simpler stack, and it makes it to where your ESCs basically just become a side part of the way if you run into a failure. You don't have to often replace the whole board,
Okay.
which is also, the downside of it, like we were talking about before. But if you're doing a fleet, having individual boards actually makes it way more easier.
So let's decode the numbers on the labels now. Like when I see something like 4-in-1, 45 alpha, 3.65, I mean, what's that telling me? Like, explain that to me.
So what you're looking at is when you hear 4-in-1, is 4 ESCs in one. And then let's go with the 45 amps. 45 amps is basically a rating of how much power in amperage the ESC can take sustained. So
Okay.
that is the maximum continuous current per channel the ESC is rated to take under test conditions that has been tested for it. And you have another part of which is a burst, like in this case, 30/40. You can go up to a burst. It can be 30. In this case, in CSC, it can go up a little bit higher. It can take a little bit over 40 amps for a little while. But typically, you want to stay at 30 amps and you have a burst rate, which is in some cases 3 to 4 seconds of burst, or not that long, maybe 2 seconds worth of burst, which just means you're going over the amount of amps that you're normally putting in. And you're basically basing this off of a rating of 50 to 75% throttle, because you don't want to go 100%, because if you need that extra where that burst could come in is where you want to be able to have a little bit more power to get up above what you need so that the power can be able to give you your altitude or push through with speed. And that's where it comes in. When you look at the battery, which is where you say 3 to 6S, that means you have a 3 cell battery, 3 to 6 cell battery, which that means that's what your ratings are capable of taking for that ESC. In the case of 3S, it means it is literally 3 cells on the battery, and they're combined in parallel to basically give you amount of power that you need in milliamps to know what you have for overall power. And the batteries go typically 3, 4, 6, and 12. And I think there's 10, but I don't really typically use those. I've never really used a 10S battery. But the ones I have used are 3S, 4S, 6S, and those are 2S also. You can go down a little bit further, 1S and 2S. So a 1 cell battery and a 2S battery. And that's what those ratings are standing for. And on ESC itself, they'll actually tell you what they can go up to. Like in this one, the 30/40 goes 2 to 6S LiPo, and it tells you what the actual battery is and allows you to know, oh, I can go with a 2 to 6S LiPo battery. In most cases, that's what you're using.
Okay. So for people like myself that are learning this as we go along and trying to configure and do builds, like if I'm running an ESC right at the rating, is that what I should be doing? Or is there some kind of like margin of error that I should be paying attention to and like be aware of?
So what you want is you want to have some headroom. And just like I was speaking about earlier, you want to think of the number, what you're having for your rating. And in real life, your amps, your ESCs are going to get hot.
Okay.
And if you're aggressively flying, that means that you're going to push those amps to be at a place to where it's going hotter. And you don't have perfect cooling. And in a lot of cases, you're just working with the ambient air flowing over whatever it is. And when you add in a heavier payload, that means that you're going to end up working with that ESC, and or the system's gonna have to push harder because it's picking up more than what it was probably wanting to pick up. So, like, to size ESCs, you your peak is expected with whatever your current rating is gonna be, and you're gonna have to do your math to make sure that whatever you need for thrust per motor equals out to how much you need to pick up your weight. So in the
Okay.
case of, let's go with this, 25 pounds of thrust per motor, which will equal up to 100 pounds that you could pick up. You
Mhm.
need to make sure that you can be able to pick that up at 70 to 80% of what your throttle rating, or, and in most cases, what I do it is 50 to 75% of my throttle. So you want to make it to where whatever your thrust is capable to be picked up at that rating. And your ESCs and motor combinations will allow you to know. It's like if you go to, as a good example, T-Motor, and we spoke about this last week, T-Motor does a great job to show you what your combination of motor ESC capabilities are and at their ratings for throttle. And that's what you want to make sure of, is that if you're going aggressive with picking up a lot of weight and you want it to be able to maintain it, you need to know what your throttle rating is going to be for it. And if you just want to fly fast, you need to make sure that you basically are under your weight significantly so that you have enough on the throttle end that you can get where you want it to go.
Okay. So with that, then where does the voltage come into play? I mean, what the 45 versus the 65? I mean, it's the same current, but a different power. Is that
Correct. So power is the voltage times current. So 45 amps is 6S is a lot more power than 45 amps at 4S. So higher voltage means you can move through the same power at lower current, which is easier on the ESCs and in on the wiring. But you also have to have the potential for bigger peaks if you overspec the motors and props. So there's a significance between a 45 amp 6S versus 45 amps 4S. And kind of we were speaking on what you need because also your wires make a difference in that too. Because the bigger the wire, the more flow and the quicker it goes versus the smaller wires don't allow it to flow. It's just like a water in a hose. The bigger the wire, the more flow it goes, and the less
Gotcha.
smaller, less flow.
Makes sense. So constricted flow. So if someone's going to upgrade from a 45 to a 65 and doesn't touch the ESCs at all, what should they be thinking about and what issues could they run into?
So one of the things that if they would want to make sure that the ESCs are actually rated for the cell count and understand that the motors may now be capable of drawing more power. And if the ESCs were already near their limit on a 4S, they may be over or
Mm,
super stressed on a 6S unless you change your KV, your props, or your flying style.
yeah, no, that makes sense. I get you. Okay, so let's talk about how ESCs and flight controllers talk to each other. We keep hearing about the PWM, the one shot, the multi shot, the DS shot. What's the difference? What's the practical difference that I need to understand?
Yeah, so PWM, let's go with that initially. Older ESCs use an analog style, which is called PWM, and that's still something that you'll hear across. If you start messing with Arduinos or Raspberry Pis or anything electronic, you'll hear that a lot because it's still commonplace in everything we do. PWM stands for pulse width modulation and encodes what your throttle can do. So typically,
Okay.
the throttle set between 2000 and 1000 with the midpoint being 1500. And that pulse width is basically what you're giving your controllers or your ESCs and your flight controller the knowledge of, hey, this is my lowest limit. And if this is in my top limit, you're going to flow between those with the PWM. So one shot and multi shot were faster analog pulses that reduce latency and were used more so for FPV. A lot of times it's still used to this day. Dshot, basically a digital signal being sent in a throttle value encoded as a digital word, basically, and which makes it more robust and easier and adds features to like telemetry in different ways like that.
Okay. So for a multi-rotor build, is there any reason not to use the D shot?
For most modern stacks, you're basically using a D-Shot as default. You know, you can use PWM in some cases, like Fixhawk will still recognize it if you have older ESCs. But D-Shot is fast, consistent, and gives you extras like ESC telemetry, RPM filtering, and easier setups. But you do have different types of D-Shot. The D-Shot is a way of communicating to your flight controller, to the ESC, or from the ESC to the flight controller in a better way than just having just a signal going back and forth. It literally will modulate it to where you need. And the only time you'll skip this is if you're on your legacy ESCs or specific platforms that doesn't support it.
Okay. And so ESC telemetry, what are we actually getting back? Like what are we receiving?
So on something like a bi-directional D-Shot, it'll give you RPMs, it'll give you current, and can give you temperature and air flags, which that's significant. Like
Okay.
I'll be honest, those are so much more helpful because when you get a ability for it to give information and then it shoots it back saying, hey, your RPMs at this, when you're going to look at your logs later to know what your RPM ratings were and what your current was being drawn versus not knowing that, that's a significant change. That's gold for tuning and health monitoring, especially in the commercial and fleet environment where you want to catch problems before they become failures.
Okay. So let's go ahead and move on to like ESC firmware and features type things, right? So on the firmware side, what are the main flavors people will get to see or experience or, get into?
So firmware is kind of similar to the P-Shot, D-Shot one of those. Those protocols still pretty much same. But in the multi-rotor world, you'll mostly see BL-HELIS and BL-HELI-32. That's your priority for closed source firmware on certain industrial type ESCs, or in this case, commercial. The BL-HELI-32 runs a 32-bit MCU and supports more advanced features like D-Shot. And then telemetry, configuration, startups behavior, and various protections So that's kind of what it's going into. So Josh, in that case, what kind of protections you think we're talking about in that case?
Yeah, I mean, actually, I was about to ask you that same thing. Like, when you mention protections, like, what am I being protected from? Is it signals? Is it the protection from outside interference? Like, what are we rolling into here when you bring up protection?
So when we look at it like that, this kind of go into the clarity of it. These are things like over temperature, low voltage cutoffs, and desync protection. I had an example of an aircraft one time we were running into. I was building an aircraft that was a octocopter that needed to pick up at least 25 pounds of weight. And it was able to pick it up, but we were running into a problem where as soon as it got in the air and it was flying, about 5 minutes later, certain motors would cut out and it literally had a couple crashes. Well, when we were looking at it and got on the ground and you started to back up, it was like they're running with no problems. Typically, a ESC goes out, it goes out completely. And at the time, that's what I knew of. But in the actuality, I was realizing like this was the ESCs we were using. It had a over temp protection on it or over current protection also. Whereas if it got too hot because there was not enough airflow over the ESC, it would shut itself down to protect it from being burnt out and protect the rest of the system from getting fried. And what was happening is once we because I had them running through the carbon tube, what I did was I pulled them out of the carbon tube, put them on top of the tube, and just in the wake of all the air that flows from off the prop, and that air coming off did enough to cool it down to where I was able to get that aircraft flying very well and way more efficient than it was before. So that's what it is when you hear over temp and current protection. And desync protection is where it allows it to where if the ESCs are not in line with what's being coming in. So say the signal is coming in and you want them to kind of communicate where it kind of drops off and now the signals are not there. It means that it won't allow to get any other signal that's not supposed to. And
Okay.
this is how well they work depending on the implementation of it. But the point is modern ESCs are doing more than just switching phases. They're also trying to protect themselves and your hardware and the rest of the build itself.
Okay, so are there any settings in the ESC firmware that you think people might be overlooking or that they need to be paying more attention to?
Yeah, so like timing settings, current limits are often left for the default. You really want to know what they are. So you want to do your research on those and making sure that you're where you need to be because it helps to eliminate the noise and making your aircraft flow and work better. For most casual builds, that's fine to just not really worry about it. But if you're pushing a specific motor or prop, and the combination too hard, those parameters make a difference between a reliable setup and one that overheats over time.
Okay. So let's move on and get practical like we did in our last episode with the motors. How do you match your ESCs to the motors, to the props, to match the mission profile that you're working?
Yeah, and before I go on, I want to cover something that a little bit I meant to say on the last one, which was something like this also. Some ESCs have their own setup and settings. Like the Castle 3040 ESCs have a capability of being plugged into a separate module and have a program that you can run that you can go in there and do your settings on top of, whereas typically you have to change the direction of the ESC by setting up and pulling two of your cables and switching them over. They go on one for one, and that will give you one specific direction. May not go the direction you want to. Typically, if it's going the opposite of what you want, you normally want to go and swap over and cross one of the three lines over, and it'll actually now make it go the opposite direction. Whereas this ESC has a capability where you don't have to do any of that. You just go into actual firmware, into the software in it, and you can change the direction. Or in their case too, it has a thing where you spin it and it'll actually change the direction that you spin once you set it, which is significant for ESC. But knowing those things on what your ESC actually runs is a good one. But kind of going back to what you were saying,
Yeah, so I asked, how do you match the ESC?
when you start from the motor and the prop side, it is an estimate, or you can look up the exceptional, expected peak or current per motor at your voltage and prop size. Once you know that, you can pick the ESC that can handle that current with that margin. And then check the ESC and firmware and the protocol support so that the flight controller and its features match as you need it.
So, can you walk us through a couple of example builds to how this might work out?
Or so if you have like say a 5-inch freestyle FPV drone on 6S with its typical 2207 motor, 2208, whatever you want to pick, and your props might peak around 35 to 40 amps per motor in a hard punch. So you're looking at say at least 45 amps with a 4-in-1 ESC. So you want at
Okay.
least a 45 amp ESC to meet the requirements for that. And it's just the higher the ESC, the more power you can push out, but also that means the more power that you're utilizing. 45 amp 4-in-1 ESC is ideal for what you need for your system not to overheat. And for, say, a heavier 7-inch long range rig on 6S, you may want to put it at a 45 to 55 amp because your ESCs are aimed to keep your sustained current well below that for a time period that you need it to.
Okay. And for a mission of, say, mapping or an inspection platform, what are we looking at?
So on a mapping rig, this is where the mission is a long, steady cruise speed with occasional climbs as needed. I'm less worried about the short spikes of needed power and more about sustained current and thermal behavior. So basically what it means is I want the ESC to stay cool and cruise along on a normal power rating and maybe even integrate logging in that case for more information later on, even if I don't need it right then. So you can monitor performance over time.
Okay. So, how does environment factor into all this? Like a hot location or high altitudes, like those kinds of things. Does that have any effect? And what kind of effect does it have if it has one?
Yeah, significantly. Like altitude, you would be surprised at how altitude changes a lot, temperature changes a lot in how your aircraft can work. I've been in places where, a altitude of say Huntsville, Alabama is way lower than the altitude in Albuquerque, New Mexico, where I was flying at almost near sea level. My aircraft get 2,500 feet and back with no problem. Whereas I'm in Albuquerque, New Mexico, and aircraft would barely get to 1,500 because it is way higher and that density altitude is way more of a hindrance on the aircraft than it is at sea level. So
Mm.
when you take hot ambient temperatures and thin air, both heat and thermal margins turn into a problem for that aircraft, and you have to take into consideration. Most people they don't even think about that unless you're like an aerospace engineer where you think about altitude because your ground level versus your altitude level is two different things. And in those conditions, it's more conservative in what your ratings are going to be anyway. Pay attention to the SC's placement for airflow and ensure that the system is set up in a way where you can keep it cool so that you don't have to worry about heat on any of the components, but you can put it in a place where you can protect it to keep it warm in the winter months too. So in the summer, you don't want anything to overheat. But in the winter, you don't want it to also lose that heat. So you need to take in consideration of how and where you place your components and what you want to do to adjust to each area where you're flying between hot locations, even high altitude, cold locations, or low altitude, sea level locations in the summer and low altitude locations that are in the winter and a cross between both. Whereas you're going from 1,000 to 1,500 to even higher. Typically from ground level to 1,000 is not that bad in a low MSL low area or low altitude location. But if you're going way above it, 5, 6, 7,000 feet up, you still now have to take that in consideration. Heat will make a difference and cold air can make a difference.
Okay. So let's move on to like some common ESC failures. Where do people most often get into trouble with ESCs? Because when ESCs fails, it's usually happening like right in the middle of your flight.
Yeah. Number one is underspec ESCs. You're saving money or you're saving weight running ESCs pretty much right or beyond their realistic limits. And when you do that, that's how you get a random mid throttle failure and your ESCs don't work. But you don't want to get an ESC that's too cheap because it may not actually be able to maintain the flight you want to because without the proper protocols to communicate back, it's not as efficient. Some of the things that flight controller may be capable of doing, it won't meet what you need. If you're flying a plane, FPV plane, you may not need a whole lot. You could get a simple, cheap ESC that only does just throttle because the only process it has to do is turning what the throttle is coming from your receiver into a signal to say, I need you to go faster or lower. And your aircraft does more, or your plane does more of the work for you because it's using the aerodynamics from the wings to get it to give lift. Whereas on a multi-rotor aircraft, that ESC is needing to do a lot of the work for the flight controller and for the aerodynamics of the aircraft. So the ESCs being put in place are getting too hot and not meeting the needs of what the actual build does.
Okay. So for me, what I just heard is translation is, yay, I saved $10, but it might have cost me my aircraft because I didn't use the right ESCs.
Yeah. And that's exactly what it would be. You're pretty much in a position where if you put cheap components on, you get a cheap response. And depending on your response of what your look or what your build, you build for intent to what you're doing. So that's the biggest thing.
All right. So we've covered the brain, we've covered the muscles, and the power translator. What's next, Vince?
So on the next one, we're moving into the radio and understanding what it needs to do.
Okay. So everybody, remember, subscribe, like, follow, all the fun stuff. Drop a comment and tell us what ESCs you're running right now. What brand, what ratings, what firmware are you using to make your system as optimal as possible? Let us know. We'd love to interact with you guys.
Yeah. And if you want more news and anything that is coming out going into the industry in the sUAS world, hit like, subscribe, and share with all your friends and people that you know may even add to the conversation.
Yep. I mean, you're watching the Swan News. We look forward to seeing you in part 4. Thanks for watching.
Thanks. Bye.